Hi everyone, my name is Nasim and I'll be presenting a paper on efficient learning of PDEs via Taylor expansion and sparse decomposition into value and Fourier domains. Sparse signals and matrices where majority of the elements are zero offers several benefits in computation. Sparse signals can be stored efficiently in the memory and computations with sparse matrices can be optimized greatly. Sparsity can also help improve scalability of machine learning algorithms and accelerate the learning of physics models from data. In this paper, we focus on accelerating the learning of physics models, specifically partial differential equation models, from data by exploiting sparsity property of the relevant signals. Physics models encoded with partial differential equation are used to model many natural phenomena such as heat equation, fluid dynamics, microstructure evolution in materials, etc. Parameters of PDE physics models can be learned by doing first simulation, match the simulation output with ground truth, and with the loss function, and then backpropagating the error gradients. Such parameter learning can be computationally expensive with increasing space and time resolution of the system due to millions of interacting points in space-time. For a particular class of PDE models called sparse and decomposable PDE models, such parameter learning can be accelerated using techniques such as random projection, locality sensitive hashing, etc. And the key limitation of such accelerated learning is that the corresponding PDE models have to satisfy two properties. First, the system state change over time has to be sparse, and second, the temporal system change can be decomposed into inner products of spatial feature functions and parameter functions. An example of such PDEs is the phase field model of grain growth in engineering materials. The change in the different grains happen only in the small grain boundary areas, so the changes are very sparse. And this change can be written as the sum of special feature functions weighted by the parameters of the PDE model. The research question that we ask in this work is, can we go beyond this assumption and accelerate the learning of PDE models that do not necessarily satisfy these properties? To this end, we propose REAL, random projection-based efficient learning, which can expedite the learning of PDEs beyond sparse and decomposable PDEs. REAL uses a combination of value and frequency domain signal decomposition, polynomial approximation of complicated feature functions, and random projection-based signal compression. Our key idea is that many dense signals in value domain can be represented as sparse signals in value and frequency domain, and complicated feature functions can be approximated with polynomials, which then makes the PDE model decomposable. The intuition behind a sparse signal decomposition comes from the observation that in many physics systems, often a very small area will undergo sharp rapid change, while large background areas changes slowly. For example, during the sintering of powder compacts into dense solids, powder grain boundaries changes only at the boundary, while temperature of the whole material changes throughout the area. Another example is the phase field model of nanovoid defect evolution in materials under irradiation. During the nano-size void defect evolution in irradiated materials, the vacancy defect concentration changes sharply at the void matrix interface while changing gradually in the surrounding region. Let's take a closer look at this. In this figure, we see delta CV, which denotes the change in vacancy concentration in a system with a single void defect, which is the circular region in the middle. In value domain, the change in the vacancy concentration is the sum of sharp changes around the circular void defect area and gradual change in the surrounding area. We then look at this change in the frequency domains as well and see that sparse signals becomes dense in frequency domain and vice versa. The key thing to note here is that the dense background change becomes sparse in frequency domain, and thus the whole 2D signal can be represented as the combination of two sparse signals, one in value domain and second in the frequency domain. With this observation, our algorithm for value and frequency domain signal decomposition follows. We start with a signal and then first apply Fourier transform on the signal. From this Fourier transform, we retain the high magnitude frequencies. For the remaining frequencies, we convert them back to value domain again to inverse Fourier transform. The threshold beta that we see here is actually chosen from empirical testing. With these sparse signals in hand, now we can apply the same accelerated learning methods as for sparse and decomposable PDEs. We compress these sparse signals using random projection into compact representations. This compression step needs to be done only once and can be done in parallel. The reduced dimension of the signals leads to first model training epochs, which leads to overall faster learning on the PDE physics model. We evaluated our real method on two applications in material science. First is the sintering of powder compacts into dense solids. Second is the nanoscale void defect evaluation in materials under heavy irradiation and high temperature. On evaluation, we find that our real method leads to faster learning of PDE physics models, and these models show high accuracy in terms of MSE, mean square error. We can also see that on simulation, our real method with data compressed to 1% of the original dimension produce simulation output of powder density and temperature during sintering that matches very closely with the ground truth observations. For a second experimental setup, the nanovoid evaluation in irradiated materials, we can see that in the third row, that when data is compressed in value domain only, the nanovoid disappears very quickly. In the fourth row, we can see that our real method, where data is compressed in both value and frequency domain, we can capture the gradual shrinking behavior that matches very closely with the ground truth compared to the baseline. In summary, we propose a more general approach compared to the current state of the art to accelerate the learning of partial differential equation physics models. Our method uses sparse signals in both value and frequency domain, polynomial approximation, and random projection. Empirically, we showed that our method can lead to 70 to 98% reduction in model training times and provide reasonably accurate PDE physics models. If you have any questions, please let us know through email. Thank you all for your time.